Geologist with the Central Mineral Environmental Resources Science Center in Denver. Doug studies the environmental impacts due to weathering of mineralized terrain in mined areas. Doug has worked on acid neutralizing capacity of volcanic rocks and on natural terrestrial carbon sequestration potential of soils derived from those weathering of volcanic bedrocks. Doug is also involved in a lot of the GIS analysis, and if you've seen any of the geologic maps of the area, Doug has had a hand in probably a lot of that. Doug's Colorado guy, went to CSU for his undergrad, and then went to grad school at CU Boulder, and has also done work at University of Denver. So please help me make welcome Dr.
Good morning and welcome. I'd like to thank Chris Peltz with Mountain Studies Institute for inviting me to participate in this conference today. My co-authors are Barnaby Rockwell, Kathy Smith, and Ray Johnson, and I'd like to acknowledge the Central Mineral and Environmental Resources Science Center who supported much of my work in this watershed. Well, I use the term geo-environmental nexus to describe the Silverton and surrounding areas. What I mean by nexus in this setting are where multiple geologic events and processes have occurred that have resulted in a rich and varied geologic history. A wealth of metallic mineralization and alteration types have formed which weather to produce acidic conditions in the watershed that are detrimental to aquatic life. Today, ecosystems and biota are all impacted by this nexus of events. Humans were initially drawn to this area because of the geology, and they continue to utilize the land for multiple recreational purposes and for their livelihoods. This region also serves as an incredible laboratory for mineralized volcanic systems, and it's one of the most well-studied types of this type of studies on all of Earth. Today I'll give a broad overview of the geologic setting of the San Juan volcanic field, then focus in on the geology and associated geo-environmental aspects of the geology in the Silverton area, and then I'll discuss some of our watershed analysis of geologic information, and then touch on natural terrestrial carbon sequestration, for which the San Juan volcanic field is important. The San Juan volcanic field is located on the eastern margin of the Colorado Plateau. The Colorado Plateau acted as somewhat as a micro-continent that was relatively undeformed, and along the edges of the Colorado Plateau, it probably served as a zone of weakness where multiple tertiary caldera, volcanic fields with calderas formed. The San Juan volcanic field is characterized by intermediate composition volcanic lavas that formed first, the big constructional plateau, then silicic calderas formed later, silicic intrusions, and also basalt and rhyolite bimodal rocks formed during Rio Grande rifting in a transition to an extensional tectonic setting. Now we'll focus in on the San Juan volcanic field geology. And as you travel north from Durango, you traverse a sequence of Mesozoic sedimentary rocks in green, and then you go down section into older rocks, Paleozoic sedimentary rocks in blue. And those are deposited on an erosional Precambrian crystalline basement surface. The Precambrian rocks are in purple. Several towns are labeled for geographic reference. Creed to the east, Crested Butte to the north. Here we are in Silverton and Durango. The San Luis Valley, the San Juan sedimentary basin to the south is a very important region for natural gas. And the San Luis Valley, which is part of the Rio Grande Rift, is important for agriculture and groundwater resources to the east. The San Juan field is important for water recharge area to the Rio Grande, Gunnison, and San Juan River basins. Considering models that predict greatly reduced precipitation in the coming decades to the southwest United States due to climate change, this water recharge area is incredibly important and critical to supplying surface water to this area. Shown here are basins outlined in black, and they intersect varying geology, lithologies. And this will become more important as I talk about the GIS later in this talk about how the geology affects water quality. The Silverton area occurs along the Colorado Mineral Belt, which is a laramide structural feature that is thought to have formed along a reactivated northeast trending Precambrian crustal zone of weakness. Metallic mineralization occurs along the length of the belt. Now I'll show caldera-forming eruptions in the order in which they formed: the San Juan Uncompahgre caldera, nested Silverton caldera, Bachelor, Creed, and Lake City calderas. Multiple other calderas that form throughout the San Juan volcanic field are not shown here. This Google Earth image shows very well the elongate, dumbbell-shaped San Juan Uncompahgre and nested Silverton and Lake City caldera complex. The San Juan caldera erupted an immense 1,000 cubic kilometers of magma, dwarfing historic volcanic eruptions. The Silverton caldera was much smaller, erupting only 25 to 50 cubic kilometers of magma. And now we'll focus in on the geology of the Silverton area. Tertiary and sedimentary units in purple and green occur south and west of the caldera margins. The Paleozoic sedimentary units in blue are shown here, and they're deposited on the Precambrian surface, the tan rocks here, south of Silverton and the Animas Canyon and Cunningham Creek. The major Paleozoic units that are important in this region especially are the Pennsylvanian Hermosa Formation and the Permian Cutler Formation. These units are important because they have limestone units and calcite cement that provide acid neutralizing capacity. The Precambrian to Mesozoic units are not exposed in the caldera because they are downfaulted during caldera formation and then covered up by tertiary volcanics. The rocks in pink over here are the intermediate composition volcanic clastic rocks and lavas of the San Juan Formation, which are part of the constructional plateau of the volcanic field. The large area depicted in peach here are the intermediate composition volcanic lavas of the Silverton volcanics that infilled the San Juan caldera. The interior of the caldera was domed and new magma pushed in, and this caused the Eureka Graben to form. These are rocks in green, lime green, are Eureka tuff that were erupted from the San Juan caldera, and when the Eureka Graben formed, it dropped down the younger lavas adjacent to the Eureka tuff. The northeast trending faults of the Eureka Graben, as well as northwesterly trending faults southeast and northwest of the caldera, served as float paths for mineralizing fluids. And post-caldera collapse granitoid intrusions, shown here in kind of this brownish orange color, formed along the periphery of the Silverton caldera. late-stage felsic intrusions, shown in red here in the Red Mountain District and other areas, drove hydrothermal systems that intensely altered the country rock and deposited metallic minerals. Areas in yellow are superficial deposits that cover 27% of the study area. Well, most all of the igneous rocks in this area have been hydrothermally altered to some extent. The rocks depicted in green here are propylitically altered rocks, and they're overprinted by more intense alteration shown in brighter colors. And as I go through the talk, I'll discuss mineralized areas and specific alteration types of each of these mineralized systems. The Mount Molly copper moly porphyry system, South Silverton mining district with polymetallic veins, the Sunnyside Eureka Graben area with polymetallic veins, the Red Mountain, Ohio Peak, and Anvil Mountain systems, acid sulfate alteration. The Mineral Creek and Animas River demark the outline of the, weathered along the outline of the structural margin of the Silverton caldera. Well, perhaps the most important rock type in this area are the Silverton volcanic lavas that infilled the San Juan caldera depression. The oldest of these lavas is the Burns member, which occurs low in the section, just right up here at the base of Boulder Mountain. And going up section, you get into the pyroxene andesite member, and then the Henson member that interleaves with the pyroxene andesite member. These units contain chlorite, calcite, and epidote in various proportions. These rocks have a typical greenish hue in outcrop and hand sample, and this is largely due to the presence of chlorite and epidote in these rocks. In the upper right, we have Burns member. It has a really strong green color because of the chlorite and epidote. The lower left is a pyroxene andesite member that tends to be very dark, and it has mainly chlorite and calcite and characteristic hematite veins that occurs along the fractures. Well, the propylitic rocks are important because they provide acid neutralizing capacity, and this is largely due to the presence of calcite and chlorite in these rocks. On left, we have Eureka tuff. Pumice biome has been replaced by chlorite. Calcite is stained with a chemical alizarin red that really makes the calcite show up well. And on the right, we have the pyroxene andesite lava. Calcite stained with alizarin red shows the calcite vein. Calcite's flooding the matrix, and there's abundant chlorite in the matrix. Well, where intense alteration is, where the propylitic assemblage is overprinted by intense alteration, you obliterate the acid neutralizing capacity of those rocks, and you generate net acid production, NAP. I'll refer to NAP throughout this talk. Pyrite weathering and pervasively altered and mineralized area produces sulfuric acid, NAP, which leaches metals that is toxic to aquatic life. And now I'll show some specific examples of those more intensely altered areas. Here we have polymetallic veins along the Eureka Graben that are exposed to silicified ridges that can be traced for thousands of feet on the surface along strike, and also thousands of feet vertically in the Sunnyside mine, for example. The white mineral in outcrop is quartz. The black staining is due to oxidation of manganese minerals that is prevalent in this Eureka Graben area. The vein surface trace is shown with the dashed line. Well, here we have examples in hand specimen of the Sunnyside ore that extracted base metals, copper, lead, zinc, and gold and silver along the Eureka Graben and related faults. On the left, it's hard to see, but these are pink minerals, pyroxmangite, manganese silicate, and rhodochrosite, manganese carbonate. On the right, we have a banded sulfide in quartz phase. The sulfides are galena, sphalerite, and chalcopyrite, and they contain abundant copper, lead, zinc, and cadmium. Well, quartz-sericite pyrite veins are exposed in several parts of the watershed. Intense alteration mainly affects a narrow zone right along adjacent to the vein, within a few feet adjacent to the vein. And where unmined, the pH of the surface waters in these areas may not be acidic because the country rocks are not really highly altered. The vein trace is showed with a red dashed line. Well, here's a photomicrograph of a lava that has been replaced by quartz-sericite pyrite alteration, and it takes this lava and it changes all the minerals to pyrite and sericite. On the left, it's a reflected light image. The pyrite is the bright mineral here. On the right, we have, in crossed polarized light, we have sericite, which is a fine-grained mica, and it's all the light colors, it's replacing the blocky feldspars of the lava. Alteration near Mount Molly, up Mineral Creek, is pervasive, and it affects the entire mountain block. You can see it here shown in the oranges and reds. The Mount Molly system is zoned outward from quartz-sericite pyrite to weak sericite pyrite to propylitic alteration. And this alteration has very high dissolved iron and aluminum in surface waters and molybdenum, and it has relatively lower concentrations of zinc and copper. The concentrations of zinc are higher on the periphery of the system because zinc is somewhat more mobile and it is dispersed outward from the zone of more intense alteration. There's a high vein density known as a stockwork that forms in the QSP alteration of Mount Molly quartz-sericite pyrite area of the Mount Molly system. The veinlets here have molybdenite, and the entire rock has pervasive pyrite throughout. The Red Mountain Mining District near Red Mountain Pass is typified by chimney-shaped silicified breccia ore bodies. This was one of the first districts to be mined here in the late 1870s. The area is part of an acid sulfate system and contains minerals that are high in arsenic, copper, and silver. There's a relatively high arsenic signature in Mineral Creek waters that can be in part attributed to the weathering of the acid sulfate system in this area. Here we have another example of the acid sulfate system. This is up in Upper Prospect Gulch, and the greenish yellow rocks stained in the foreground are jarosite, potassium aluminum iron sulfate. That's an indicator of pyrite weathering. The pyrite weathering is also indicated by these areas in brown and red and the high peaks. The white areas are bleached from interaction with hydrothermal fluids. Minerals typical of the acid sulfate system include abundant quartz, pyrophyllite, aluminum silicate not shown here, and abundant alunite, potassium aluminum sulfate. Here's a hand specimen of a pinkish alunite. Here we have a porphyry where alunite is replacing blocky feldspars. And on the periphery of the more intensely altered part of the acid sulfate system, you get an argillic assemblage. And this mineral is a dicite, a white waxy clay mineral. Well, the highly altered and pyrite-bearing rocks that I've shown previously experience hydrologic weathering and result in transport of metal cations in solution. The metals precipitate in superficial deposits, and where they're high in iron, they form ferrocrete deposits, and high in manganese, they form manganocrete. These deposits have been dated between present to 10,000 years before present, so they are an indicator of acidic conditions that have been ongoing in the watershed for many years prior to mining and concurrent with mining. They're in one sense nature's way of sequestering metals. Iron bogs and springs are strong visual indicators today of the ongoing transport and precipitation of metals in the watershed. Multiple weathering processes affect the mobilization, transport, and fate of the metals in the environment. Here are a few examples of the many processes that are ongoing. Upper left, we have pyrite that has been weathered out of iron that's been weathered out of pyrite-bearing rock. It's precipitating at the air-oxygen interface at stream level of Mineral Creek. Below we have iron that's precipitating out of a very acidic stream. It's intersecting a stream with, that's less acidic, and it's precipitating the white mineral here, which is aluminum sulfate. Here we have shallow groundwater that's infiltrating an alluvial fan that's derived from quartzosite vein material containing pyrite. And all these things basically affect water quality in this environment. Instantaneous storm events accelerate weathering of the hydrothermally altered areas and can cause large pulses of metals and total dissolved solids into the streams, and they can confound remediation efforts. Here, outlined in red, is a debris flow in Topeka Gulch that formed in one such event, and Mineral Creek is, Cement Creek is loaded with total dissolved solids and intersecting Animas River, which is relatively clear during this storm event. Well, mining basically overprints all the natural weathering processes. The mining, as we all know, is a long legacy, over 100 years in this watershed, and so I wanted to show some examples of ongoing draining adits, which are a major issue, as we all know, here in the watershed. Another example of how mining has impacted the environment is shown here. This geochemical profile, younger deposits, gets younger up in this geochemical profile. But you can see when milling started, there's above the blue line, there was a spike in metal concentrations, and that was attributed to milling near the Eureka town site. Prior to mining, you'll notice that, or prior to milling in this area, you'll notice that especially copper, lead, and zinc were still relatively high, and that was due to the base metal sulfides that were weathering out of the system prior to milling. Hydrologic weathering and the water rock and mineral interactions are ultimately responsible for the water quality we see in the region today. The flow lines shown in blue on the diagram from Jonathan Kane and Anna Wilson with USGS. And what this conceptual model shows very well are the multiple flow paths, shallow to deep. Water infiltrates as snow, and it interacts with the shallow and alluvial colluvial material here. Or it can take a much more tortuous and long path through fracture systems and basically the water quality that is evolved along these flow paths is going to be a direct result of all the different materials and the compositions of those materials that the water interacts with along the flow path. And now we'll discuss some of our GIS analysis that we've done in the watershed. And what I'd like you to keep in mind is in this watershed we have a balance of those acid neutralizing capacity rocks from the propylitic assemblage, and then those net acid producing rocks where they're more intensely altered with abundant pyrite. And then factored on top of all this, we have the mining impacts. So all of this is affecting water quality in these watersheds that we're analyzing using GIS. What we've done is we used a GIS processing approach where we've taken digital terrain, defined a hydrologic network, defined watersheds, and the watersheds are the analysis areas that we intersect with other geo-information types, such as alteration especially, and that's what I'll be focusing on in these examples. We've used 3 different remote sensing data sets to map alteration. And we've used Landsat, TM, Aster, and Avarice. And the Avarice provides the most complete alteration mapping. And that's largely because we filled that in with field work to interpolate basically all of the bedrock alteration types. Just using simple GIS and analyzing the alteration data set, we find that the preponderance of rocks here are propylitically altered. 88% have some ANC, and they're overprinted by more intense alteration at only 12%. So it's very illustrative here that we have a very small percent of NAP rocks that cause a lot of detrimental problems to water quality. So it doesn't take much, especially when it's overprinted by mining effects. Here we have the percent propylitic alteration for acidic watersheds, which have 44% ANC, acid neutralizing capacity rocks. And then the neutral watersheds have 77% propylitic ANC rocks. And so you start to see this balance of what's causing the acidic conditions or neutral conditions in watersheds. And the average elevation of those ANC rocks tends to occur higher than the median elevation in that watershed. Here we have the area of NAP rocks in watersheds that are acidic. And the red arrows delineate those watersheds that don't have NAP rocks. So what's going on here? Well, in this case, they're draining adits that strongly indicate there's a mining impact. And in many of these, they're draining adits that are causing the acidic conditions. Well, this watershed approach is pretty simple and pretty neat, because we have an incredible water quality data set collected at base flow conditions, where we've sampled the watershed outlets, and you can see the different alteration types. This is Prospect Gulch and adjacent Georgia Gulch, and all these different colors represent the different alteration types, and they're widely different. And that controls the outlet water chemistry. We have very acidic conditions and high metals in Prospect Gulch, and not very acidic conditions in Georgia, and low metal concentrations. So what we've done is we've used this data and done simple linear regression analysis for multiple watersheds and areas, in this case, area of QSP alteration and pH. And we've done this for multiple parameters and multiple alteration types. And QSP tends to be one of the most important that shows up as controlling water quality, with a pretty good correlation between area of QSP and a negative correlation with pH. So as you get more QSP alteration, you get more acidic conditions. And with simple GIS analysis again, and pretty basic data, just pH, area of alteration type, and with some knowledge of whether a watershed is mining impacted or not, we've been able to group these watersheds based on their characteristics. And the watersheds in green are big, broad catchments. They tend to have a large amount of acid neutralizing capacity rocks. They are less acidic, pH 5 to 5.21. Then we have, these colors are kind of hard to see, but at the bottom we have, on the other end of the spectrum, we have watersheds that are mining impacted, and they tend to have a high net acid production area, and they're very acidic. So from a reclamation standpoint, these broad open catchments where they're even mining impacted and they have low pH and some acid neutralizing capacity rocks, those would be the ones where if new mining were to occur, you may not have as much of a reclamation challenge in those types of watersheds compared to the worst case scenario, such as Prospect Gulch is one, where you have heavy mining impacts, high area of net acid production. So that would be probably the most challenging reclamation scenario, or if new mining came in, those would be the areas that would pose the greatest challenge. These images show surface water quality in relation to pH. And what I'd really like you to clue in on this particular slide is the South Silverton mining area. The pH is near neutral, despite polymetallic veins that are weathering. There are other metals that are an issue in this area, but it's pretty illustrative of how the bedrock alteration geology controls water quality. Here we have zinc toxicity. Again, we'll focus in on that South Silverton mining area where there's no zinc toxicity in these streams. This is from Besser and others, 2007. South Fork Mineral Creek, no toxicity. Most of the other parts of the catchment, with a few exceptions, such as east of Cement Creek, where there's a lot of propylitic rocks, there's acute toxicity to sensitive taxa, or toxicity in red to brook trout downstream from the more intensely hydrothermally altered areas. Well, the question of the day is, where do all the trout hang out in this watershed? And many of you may know this, but not surprisingly, because of the propylitic rocks, we have trout in the South Silverton mining area and along the Animas River and South Fork Mineral Creek. But you notice all the areas in red, they were devoid of trout during this survey where Besser published in 2007. Now I'd like to talk with you briefly about the concept of natural terrestrial carbon sequestration. This work was in part spearheaded by Alison Burchell with the NTS group. She is the driver behind a lot of the thought that went into this whole idea of NTS. And natural terrestrial sequestration is how basically the Earth's soils, how it sequesters carbon, using, looking at all the biogeochemical, geologic, weathering, vegetation, processes that all come to play into the soils storing carbon, and they do so in a great fashion. 2 gigatons per year over the entire globe. The soils are an incredible carbon reservoir. So looking at the Silverton area, we've analyzed mine waste, and not surprisingly, it has 0 weight % carbon. This has been reclaiming nearly 100 years on the left. And then we have another mine waste pile close to town here, and it's started to reclaim after a few decades after reclamation. It has 1 weight % total organic soil carbon. And on the right, we have this very incredibly rich, healthy soil derived from weathering of propylitically altered rock, and it has 24 weight % total organic soil carbon in the O to the A horizon. So from a reclamation standpoint, this would be the end member of how do we reclaim this mine waste to get to this point. And through NTS types of thinking, I mean, this is a challenge, but we can learn from this, which is reclaimed after logging and mining in the area, to a very healthy soil system. So what factors influence NTS? Well, there's the ANC rocks, the propylitically altered rocks that we've been talking about. Here's on Engineer Pass. The red line denotes mine waste devoid of vegetation to the left, and then right along the margin there's grasses that are starting to reclaim. And that's ANC rock that's piled up over on the mine waste. So this is helping to start the soil formation process by reducing the acidity. Another thing that you'll be hearing a lot about this in this conference is biochar. And in the soil profiles that we've taken throughout the Silverton area and the Western Rocky Mountain Cordillera, we find burn horizons that are from forest fire events, and they're analogous to the biochar. And the biochar could provide soil moisture and nutrients that are released to plant roots, and they could basically store carbon, and they don't break down within millennia. We've dated charcoals between 500 and 5,000 years. These are old and stable carbon pools that are part of the whole total organic soil carbon. Other things that affect NTS are mycorrhizae from fungus and other plants, soil aggregates that hold on to carbon and don't release it to hydrologic weathering, the ecosystem, the precipitation, elevation, mineral carbonation reactions in these mineralized systems could be very important in storing carbon. And we believe that this is a very important concept that needs much more further work and understanding about how this could perhaps play a role even in mitigating the effects due to climate change by understanding more effectively these NTS processes. I'd like to thank you again for inviting me here to present this talk, and I look forward to the rest of the conference. Thank you.